Okay, so thank you everyone for tuning in. So I will talk about string graphs and the Erdős-Hajnal property. So let me first describe what the Erdős-Hajnal property is. So given family of graphs, we say that this family has the Erdős-Hajnal property if each member of this family contains either a polynomial-sized clique or a polynomial-sized independent set. So formally, there is some constant C if each member on n vertices contains either a clique or an independent set of size at least n to the c. So we all know that there exist graphs, namely random graphs, which only have logarithmic sized cliques and independent sets. But Erdős and Hajnal noticed that the moment our graph has a certain structure, we can immediately find much larger cliques and independent sets. In particular, they proposed a conjecture that if we consider a graph G that avoids some fixed graph H as an induced subgraph, we can immediately find polynomial-sized cliques or independent sets. So this Erdős-Hajnal conjecture can be stated equivalently as if there is given a hereditary family of graphs. Here, this means that there is a family of graphs closed undertaking into subgraphs. So if there is given such a family of graphs, which is not the family of all graphs, then this family has the Erdős-Hajnal property. So every member contains a polynomial-sized clique or independent set. So now this conjecture is still wide open, despite that it is extensively studied in the past 30 years. So, and also this conjecture finds its ways in combinatorial geometry, and that is going to be the main topic of this talk. So in particular, I'm going to consider the Erdős-Hajnal property of so-called intersection graphs. So what is an intersection graph? Given family of geometric objects, I say that the intersection graph is the graph whose vertices correspond to the elements of F, elements of this family, and two vertices are joined by an edge if the corresponding sets have a non-empty intersection. So now let's see a few simple examples of the Erdős-Hajnal property in intersection graphs. So the first easy example is just the classical folklore, which tells us that if we look at the intersection graph of just intervals on the real line, then this graph is perfect, which means that its chromatic number equals to its clique number, or which implies that such a graph on n vertices contains either a clique or an independent set of size at least square root n, and here the square root n is sharp. Now, another simple example is the intersection graph of axis parallel rectangles. So there is a simple divide and conquer argument which gives us that the intersection graph of n rectangles contains either a clique or independent set of size at least some constant n square root n over log n. And here it is already a challenging problem whether this log n can be removed. So it is conjectured that this maximum should be at least some constant square root n. So now let's see some more interesting examples. So it was proved by Lárman, Matušák, Pach, and Törőcsik that if one considers the intersection graph of convex sets, then such an intersection graph contains either a clique or independent set of size at least n to the 1 over 5. And also their method implies the same bound for a more general family of geometric objects which are called X monotone curves. So let me just quickly define what these are. So when I say curve, I will always mean just the image of a continuous function of a plane. So you can just think of curves as just scribbles drawn on the plane. And I say that the curve is X monotone if every vertical line intersects it in at most one point. So you can think of them as just drawing of functions. Okay. So then here immediately one can ask that how good is this lower bound n to the 1 over 5? So the best known upper bound is due to Kinchel, who proved the upper bound under the 0.405. So there is still a huge gap between the lower and upper bound, and it is open what is the right exponent. Okay, so this is about convex sets. So let's see a more general family. So, another Erdős-Hajnal type result is about intersection graph of curves. So Fox, Pach, and Todd proved that if we consider a collection of curves where any two curves intersect in constant number of times, so we assume that any two intersect at most k times, where we think of k as a constant, then this family has the Erdős-Hajnal property, where now this exponent depends on this constant k. And finally, the final result is that, which is not really about intersection graph, but still related, is this result of Alon, Pach, Pincasi, Radojcic, and Scherrer, who proved that the family of semi-algebraic graphs of bounded complexity has the Erdős-Hajnal property. So I'm not going to really talk about semi-algebraic graphs, so let me just briefly describe what this means. So if your graph can be described by, let's say, the vertices of your graph are just points in some fixed dimensional space, and your edges are defined by polynomial relations, that's a semi-algebraic graph. And if you have such a graph, then it has the Erdős-Hajnal property. And the way it is related to us that if we have some geometric objects which can be defined algebraically, for example, segments, rectangles, parabolas, ellipses, so on, then the intersection graph of such geometric objects are semi-algebraic. So for such intersection graphs, we immediately get that they have the Erdős-Hajnal property. Now, what we are going to be interested in this talk is some a common generalization of these intersection graphs, which are called string graphs. So string graph is just the intersection graph of curves in the plane. So again, a curve is just the image of a continuous function on the plane. So again, just a scribble. So it was conjectured by Alon, Pach, Pincasi, Radojcic, and Scherrer, and later Fox and Pach, that the family of string graphs has the Erdős-Hajnal property. So in other words, if we have a string graph on n vertices, then it contains either a clique or an independent set of size n to the c, where c is some absolute constant. Now, the reason this conjecture is particularly interesting is that it implies the Erdős-Hajnal property of all of the aforementioned intersection graphs. In particular, it implies it with this uniform exponent, constant exponent c. So, and also if one considers any type of geometric objects, then it implies the Erdős-Hajnal property of their intersection graphs. And the reason of this is when we talk about geometric objects, we imagine a connected subset of the plane. And any connected subset of the plane can be approximated by a curve. So in particular, every intersection graph of geometric objects is a string graph. And so what is known about this conjecture? So it was proved by Jacob and János that if we have a string graph on n vertices, then it contains either a clique or an independent set of size at least n to the constant over log n. So again, we would need that this right-hand side is n to some constants, so they get this slightly worse bound that they have 1 over log n instead of a constant. Okay, so what I will talk about today is a proof of this conjecture. And so I would like to give you some high-level proof of this conjecture. And in particular, the proof itself, my proof itself, is not very long, but the only reason it's not long is because it builds on all the previous work done by Jacob, János, and all the other researchers in the area. So in order to be able to talk about my proof, I have to describe their approach. So what I will do next, I will describe what Jacob and Janusz did, and I will talk about what are the shortcomings of their approach, and I will tell you how to fix these shortcomings. Okay, so let's see the proof. Now, one idea of the proof is that, okay, instead of the Erdős-Hajnal property, maybe let's try to prove something stronger. So maybe let's try to prove that it has the so-called Strong-Erdös-Hajnal property. So what is this property? So we say that a family of graphs G has this Strong-Erdös-Hajnal property if each member, either the graph contains a linear-sized biclique or its complement contains a linear-sized biclique. So what's a biclique? Every time I say biclique, I mean a complete bipartite graph where both vertex classes have the same size. So instead of finding a polynomial size clique or independent set, we want to find a linear sized biclique or the complement of it. Now it turns out that this strong Erdős-Hajnal property is really stronger than the Erdős-Hajnal property. So in hereditary families of graphs, this property implies the Erdős-Hajnal property itself. And in general, the idea behind it is that it should be much easier to find clique to each other or that are empty to each other than finding a clique or independent set itself. So that's the basic idea behind this approach. But unfortunately, in general, the strong Erdős-Hajnal property is too strong. So in general, if one would ask that if we replace the Erdős-Hajnal conjecture with the following conjecture, that is it true that every hereditary family of graphs has the strong Erdős-Hajnal property, then the stronger conjecture can be easily seen to be false. So one can look at graphs avoiding some fixed cycle of some small length, and then just standard probabilistic constructions show that they do not have the strong Erdős-Hajnal property. Nevertheless, if a family of graphs has the strong Erdős-Hajnal property, the idea is that it should be easier to prove that than the Erdős-Hajnal property itself. And this idea was actually very successfully used in the past 15 years. So the strong Erdős-Hajnal property was used to prove the Erdős-Hajnal property of many families, not only in combinatorial geometry, but also in structural graph theory. But let me show you some examples in combinatorial geometry. So in particular, it was proved by Pach and Solymosi that intersection graph of segments has this strong Erdős-Hajnal property. Now this was generalized to all semi-algebraic graphs by Alon, Pach, Pinkasi, Radicic, and Scherer. And in particular, for this family, they only know the Erdős-Hajnal property because they know the strong Erdős-Hajnal property. Now later, it was also this strong Erdős-Hajnal property was also proved for convex sets. And finally, it was proved for intersection graph of curves, where we assume that any two curves intersect at most a constant number of times. And again, for this last family, the Erdős-Hajnal property was proved using the strong Erdős-Hajnal property. So this also illustrates the strength of this approach. So, but then this gives you the idea. So, okay, let's maybe try to prove that string graphs have the strong Erdős-Hajnal property. So, unfortunately, this is false. And so let me explain why this is false. So it turns out that string graphs and incomparability graphs are very closely related. So what's an incomparability graph? The incomparability graph is just the complement of a comparability graph. And so what's an incomparability graph? So given a partially ordered set, you can look at if two elements are comparable, let's say x less than y or y less than x, you just forget which one is less than which, and you just draw an edge between them. This gives you a comparability graph. And so the complements of such graphs are closely related to string graphs. And so how are they related? So it's an odd result of Lovász, who proved a number of times that every incomparability graph can be realized as a string graph. So more precisely, he proved that so one can consider the following special family of curves. So here, we consider two vertical lines, and we only consider curves that start from the one of the lines and end at the other line, and the curve itself is completely contained in the strip. And if one considers such an intersection graph, then it can be easily seen to be an incomparability graph. This is true because we can define the following partial order, which you can see on the right-hand side. So let's say if we have this curve 2 and we have this curve 4, then we can say that this curve 2 is less than 4 if it is completely contained below this curve. So here I draw that 2 is less than 4. Okay, and so we see that if we have such an intersection graph, this is an incomparability graph, and what Lovaas proved is the converse. So if we have an incomparability graph, it can be realized as the intersection graph of such special curves. Okay, but now how is this related to us? So it was proved by Fox that for incomparability graphs, the Strong-Erdös-Hajnal property does not hold. So in particular, he proved that there exist incomparability graphs with no such that neither G nor its complement contains a bi-clique of size n over log n. And so this is bad news for us. But as you can see here, instead of linear size bi-cliques, we cannot find bi-cliques of size n over log n, which are almost linear. So maybe something close to linear still holds. So let me talk about this. So for incomparability graphs, Fox proved the converse of this statement. So he proved that in every dense incomparability graph, one can find a bi-clique of size n over log n. So here I say that an incomparability graph is dense if it contains some constant and squared edges. So any such incomparability graph contains an almost linear sized bi-clique. And another important observation, or not really observation, but this is a serious result of Jacob and János, is that every dense string graph actually contains dense incomparability graph. So string graphs and incomparability graphs are even more closely related. But then these first two results combined give you that every dense string graph contains an almost linear sized bi-clique. Okay, so this is good, but so this is about dense string graphs. So what can we say about sparse string graphs? So on the other hand, it follows from a result of Lee, who proved the conjecture of Jacob and János that every string graph with m edges contains a balanced separator of size square root m. So what does this mean? So here is this picture of 500 curves. Now it tells you that if the intersection graph is sufficiently sparse, then you can find a small separator. That is, you can find this small collection of curves, namely here these red curves, such that if you remove these red curves from your picture, then the remaining collection of curves falls into a bunch of parts, such that there are no intersections between the parts. But then this immediately gives you a linear size bi-clique. So if your string graph is, so this tells you that if your string graph is sparse, then you can actually find linear size bi-cliques in the complement. Now, putting these two results together, you immediately get this Almost-strong-Erdős-Hajnal property, which tells you that if you have a string graph and n vertices, then you can either find an almost linear size bi-clique in G, or you can find a linear size bi-clique in the complement. So this is all very cool, but unfortunately, this theorem is not strong enough to imply the Erdős-Hajnal property. So to get the Erdős-Hajnal property, you really need that you find linear sized bicliques. So then how can you fix this? So as you can see, one half of what you want is already here, so you can find linear size bicliques if the string graph is sparse enough. So we just have to do something with dense string graphs. And the idea is to fix this. So now we get the Strong-Erdös-Hajnal properties is too much to ask for. So maybe let's just relax this a bit, and let's ask for something a bit less. So in particular, what's a biclique is just two sets. So one is complete to the other. So maybe let's relax this by asking for more sets. So let's say that we want to find a bunch of sets such that any two are complete to each other. But in exchange, we can allow these sets to be smaller. So this motivates the following notion, which I call the Quasi-Erdös-Hajnal property. So I'm going to say that a family of graphs G has the Quasi-Erdös-Hajnal property if there exists some constant C. So, okay, so this definition is slightly technical, so let me try to say it in words. What does it say? So it says that it has the Quasi-Erdös-Hajnal property if for each member, so for each G, there exists some T. So now it's important that this T depends on the graph G itself. And not only depends on the number of vertices, but it can depend on the very structure of G itself. So now if we can find this T, and we can find T disjoint subsets x1 xt, such that the sizes of these sets are large enough with respect to T and the size of G. So we have this formula. It's not important now. And we have that either any two of these sets are complete to each other, or for any two sets there are no edges between them, then we have this Quasi-Erdös-Hajnal property. Now let me note that, so if we could always guarantee that this T that we get is 2, then this definition would be equivalent to the Strong-Erdös-Hajnal property. So this definition is really relaxation of the Strong-Erdös-Hajnal property. And it turns out that with this relaxed definition, with this new property not only implies the Erdős-Hajnal property, but these two properties are actually equivalent in hereditary families of graphs. Good. So now you might wonder then, okay, so now we have this equivalent definition of the Erdős-Hajnal property. So what do we gain by this? What's the advantage? And the advantage is that we can consider an asymmetric form of this. So namely, we are going to prove the following symmetric version of this property. So we prove that so again, we for a second forget about string graphs and look at incomparability graphs. So we can prove that for every dense incomparability graph, we can find this T, and we can find these T disjoint subsets whose sizes satisfy this condition of the definition, and also now we have that every xi is complete to every xj. But then, remembering this previous result of Jacob and Janusz, that every dense string graph contains a dense incomparability graph, we immediately get that if G is a dense string graph, then the same result holds. So now let me remark that here now this exponent C, this only depends on the density of the string graph, nothing else. Okay, so now we get this asymmetric result, and now we can put this asymmetric result together with the separator results, so with the result of Lee, to conclude that actually the family of string graphs has this Quasi-Erdős-Hajnal property. So in particular, it has the Erdős-Hajnal property, and that's the whole proof. So now I don't want to go into details about the proof of this lemma. So instead, let me just finish my talk with an open question. So I proved that if we have a string graph and n vertices, so there exists some absolute constant C such that for every n, if we have a string graph and n vertices, then it contains either a clique or an independent set of size, at least n to the C. But what can we say about this constant C? So for my proof, one can definitely calculate an exact constant C. But in order to do that, one has to look at my proof, the result of Jacob and Janusz, and also the result of Lee. And from all these papers, one has to work out the constants to get this C. So I didn't want to do this, but it is definitely possible to get a C. And I think this C one would get is not horrible. So it's definitely not going to be close to the truth, but it's not going to be horrible. So I would guess it's going to be something like 1 over 100 or 1 over 1,000, just because in the very end we take logarithms, so it cannot be too bad. But still, what is the best known upper bound? The best known upper bound is still this construction of Kinchel, which I mentioned earlier, which works for convex sets as well. So he actually just uses segments to find an intersection graph with no clique or independent set to this n to the 0.405. So this slightly bothers me that there are no better known construction, and I think this is a really good research problem to try to come up with something more interesting. Yeah, so this is all I wanted to talk about. So thanks everyone for listening.
Thank you very much, István, for a very interesting talk. Are there any questions?
What are other families of geometric objects that you would like to see for which you would like to see the proof of the Erdős-Hajnal property or this proof?
Okay, so in 2 dimensions we are done. So in 3 dimensions, it's not clear what the right question is, because if, for example, one looks at convex sets, it's known that every graph can be realized as the intersection graph of convex sets, so that's uninteresting. So it's not clear what the right question would be in higher dimensions.
Okay.
Can I ask you a question?
Yes.
Is it known that Erdős-Hajnal conjecture to be true for Cayley graphs?
So do you ask Cayley graphs?
Yeah, Cayley.
I mean, so how do you define that? Because Erdős-Hajnal is for a family of graphs, and so for example, if you look at the Cayley graphs where the generators are chosen randomly, then it's not going to be true. They have logarithmic size cliques and independent sets. So I think this is a result of Ben Green or Tim Gower or something like that.
No, we avoid the Cayley graph. So your H here is a Cayley graph. I don't know. For you fix number of generators and you avoid such graph.
I mean, if you fix the number of generators, then your graph is sparse, so you can just find a very large independent set just because of the degrees. So your graph needs to be dense, and so it needs to have like a constant n degree for this question to be interesting. Or I'm misunderstanding something.
It can be any subset of a group. So fixed size or comparable with size of the group.
Yeah. So as I said, if you pick a random set of n over 2 generators, then yeah, it's not going to be true. They have logarithmic sized cliques and independencies.
No, I'm not asking about finding clique in a Cayley graph. I'm asking about Erdős-Hajnal conjecture. So
I mean, that's the Erdős-Hajnal conjecture.
I mean, you're looking at all the graphs that avoid Cayley graphs, or
That's in the original problem.
Okay. I see. No, so there is very little known about this original form. So it's already not known if we forbid a 5 cycle, whether this family has the Erdős-Hajnal or not. So
I think for kilographs,
I mean, a 5 cycle is a Cayley graph. So.
Okay. So it's unknown. Thank you.
Yeah, thank you.
Can I ask a question?
There is a question in the chat.
Yes. So is it possible that TG is universally bounded? So what was TG? So what's TG?
That T that you defined there for every graph, if you go back on your slides. Here, this T.
Yes.
So you said it can be 2, but could it be like always at most 3?
No, so it cannot be a constant, because if it's a constant, then if you have a bunch of smaller parts and it's constant, then this x1, xt have linear size. So you would also find a linear size biclique.
Okay.
So, but I think it's true that it's always going to be logarithmic in n at most.
Yes. So do we know the set of forbidden induced subgraph for string graph? Or even better, forbidden induced subdivision of some graph?
So it's known that the subdivisions of K5 as induced subgraphs are forbidden, but I don't think that characterizes. So I would say it's not known the full list of forbidden subgraphs, but I might be wrong.
Okay. Thank you.
Yeah, I have a question. So the question is about when you consider, in some sense, an opposite property of C Ramsey, the graph is Ramsey if largest clique and the largest independent set is not bigger than constant times logarithm of n. And there is this famous conjecture that about the distribution of sizes of these graphs, of pairs of number of vertices and number of edges, that was recently proved by Sudakov and Kwan. And other something interesting for graphs that have Erdős-Hajnal property. Interesting about distribution of induced subgraphs, or it is a stupid question. I don't know why.
No, this is actually a question I also thought about. So it's more about the C-Ramsey graph. So in C-Ramsey, you have this very strong condition that no clique or independent set of size constant n log n, but for these statistic questions about edge numbers and vertex numbers, it seems like it's not needed at all. So already when you have, so this is a conjecture of Alon and some others, that already if your largest clique and independent set is at most some n over 8, so the some small constant times the number of vertices, then you can already find all let's say edge numbers up to the number of up to the total number of edges, constant times the total number of edges.
Yeah. Thank you.
Thank you.
Thanks, István.